Let's start module 4, and it is about the analysis of statically indeterminate pin jointed frames, and we'll be discussing the trusses using flexibility method. Remember, procedure is exactly the same. The only difference is in case of the frames, the predominant actions were the moments. So we took the moments, we wrote the moment equation, we ignored the shear and the axial forces, and while taking the moments, we considered the fluxural rigidity, which is EI value. Here, in case of the pin jointed frames, especially in case of the trusses, the axial forces will be the predominant actions. So we will be taking the axial rigidity instead of the fluxural rigidity. Now, EA value will be involved, and we will be interested in finding out the axial forces. As in case of the truss members, the moment is 0, we consider them equal to 0. Now, topics to be covered in this module, it will include introduction, prerequisites for using a flexibility method for trusses, indeterminacy of trusses, revision of unit load method, flexibility method procedure for truss analysis, and then analysis of truss examples 1, 2, and 3. And then finally, you will get the assignments. Introduction to this flexibility method. First, why we use this flexibility method to the analysis of indeterminate trusses. Again, the same 3 reasons: to solve the problem in matrix notation, which is more systematic. We write the simultaneous equations. Now, solution of the simultaneous equation is, if we go by the conventional method, it is very difficult. So first we write them in the matrix notation form, and then we solve the matrices. And especially this is easy now with the help of the computer. We can find out the support reactions by using this, and we can find out all the internal resisting axial forces with the help of this method. Now, basic method, we will go now slowly over this one. The basic method for the analysis of indeterminate truss by force method or flexibility method here is similar to the indeterminate beam analysis discussed in the previous lessons. For beams, for frames we discussed. So basically it is the same method. Now what we do in this case, determine the degree of statical indeterminacy of the structure. This is the first step. Then identify the number of redundant reactions which will be equal to the degree of indeterminacy. The redundants must be so selected that when the restraint corresponding to the redundants are removed, the resulting truss is statically determinate and stable. Now, 3 kinds of indeterminate trusses we can have. One is external indeterminate, and external indeterminacy, remember, it is related to the support conditions. How it is found? It is equal to the number of unknown reactions minus the available equations of equilibrium. Number of unknown support reactions, so it means it is relevant to the support reactions. So in case of external indeterminacy, select support reactions as redundant actions. So if a structure is externally indeterminate, we need to now select support reactions as redundant actions. And if it is internally indeterminate means the number of internal actions, the member actions are more whatever is required for the determinacy. So in case of internal indeterminacy, selection member forces as redundant actions. So in case of internal indeterminacy, we select the member forces as redundant actions, and how the structure is made internally determinate. We cut that member. We release the member force. Now we'll discuss this. And if a structure is externally as well as internally indeterminate, which we call total indeterminacy, then the structure is the redundant actions are taken as support reaction as well as the member forces. So external indeterminacy with the support reactions, internal indeterminacy with the member forces, and the total indeterminacy depending now. So it will be the summation of support reaction as well as the member forces. Now, prerequisites for analysis with flexibility method. Again, one must be having enough concept of matrix algebra, must be able to find the statically indeterminacy of trusses, concept of methods for finding displacement. So unit load method for displacement here we will be using, and must be able to analyze a determinate truss. Now remember here you will be having a lot of computations now, a lot of calculations. So here you cannot afford taking joint for the analysis of each members and going joint by joint, because that will take a lot of time. So most of the members you should be able to analyze by observations. And in some cases, if you need the method of joints, you can apply, but for the whole structure, for the whole members, it will become very time consuming. So you should practice the analysis of determinate trusses and should be able to find out a shortcut how we find out the member forces, the magnitude of the member forces and their directions also. I'll show you how we can do it. Now, indeterminacy of trusses we are covering. This you must have studied this in your previous semesters. Now, the truss is said to be statically indeterminate when the total number of reactions and the member axial forces exceed the total number of static equilibrium equations. So statical indeterminacy, which is the total indeterminacy, it is equal to m plus r minus 2j, where m is the number of members, r is the number of support reactions, and j is the number of joints. So from this you can find out the total statical indeterminacy. But remember that if you know the total statical indeterminacy, it does not tell you how much it is externally indeterminate and how much it is internal indeterminacy. Why? That is important. Knowing the external indeterminacy and internal indeterminacy separately, that is important. And the reason is, if it is external indeterminate structure, you need to release the support reactions accordingly. And if it is internally indeterminate, then you need to release the member forces accordingly. So separately, you will have to find out the external and internal indeterminacies. So from now, the addition of the member plus reactions, it must be equal to twice the number of joints. Why twice the number of joints? Because it is a plane truss, and in plane truss at each joint, two equilibrium equations are available. That is summation of fx is equal to 0 and summation of fy is equal to 0. So if they are equal, the structure is statically determinate, and if m plus r exceeds this minus 2j, then it means that will give you the number of the degree of statical indeterminacy. Here is the explanation to the different terms where m, j, and r the number of members, joints, and unknown reaction components respectively. Now, types of indeterminate trusses. There are three different types of statically indeterminate trusses. Internally indeterminate trusses, where internally I means internal indeterminacy, it will be found from m plus r minus 2j. M plus 3 minus 2j, m plus 3 actually, this is not m plus r, m plus 3 minus 2j. These are the available equations in case of the trusses as a whole. External indeterminacy, it will be r minus 3, ei will be equal to r minus 3. Now, if we add these two, internal indeterminacy and external indeterminacy, so 3 and 3 will cancel and we are left with m plus r minus 2j, which is written here for the total indeterminacy. This is how we find the external, internal, and total indeterminacy. Now, internally indeterminate trusses, again, the same thing, internal indeterminacy. Here we are discussing that it will be equal to m plus 3 minus 2j. Here you can see external indeterminate trusses, it will be r minus 3 simply. And the total indeterminacy we can find out by m plus r minus 2j. So here is that condition. Now let's take the example of this truss. Now we have a truss having the nodes or these joints A, B, C, D, E, F. Means we have how many members? The bottom card, if we see 1, 2, and 3, top card 1, so 4. Then we have these web members, the diagonals and the verticals. So these are 6 now. So 6 plus 4 is equal to 10. M is equal to 10 recorded here. Number of reactions will come, support reactions will come from the support. So at A we have hinge support, at D we have hinge support. So at each hinge we have the capability of horizontal and vertical load and horizontal and vertical reaction at D also. So 4 are the these support reactions. So R is equal to 4. Number of joints A to F, so 6 joints, so J is equal to 6 now. To find the internal indeterminacy, it is m plus 3 minus 2j. M was 10. 10 plus 3 is 13 minus 2 times j is 6, so 12. It is 1 degree. Internal indeterminacy 1 degree, so we need to cut one member now to release the member force. External indeterminacy r minus 3, r was 4. So 4 minus 3, 1 degree. So it means we need to release one support reaction in order to have externally determinate structure. Total indeterminacy m plus r minus 2j. So 10 plus 4 is 14 minus 2 times j is 12. So 14 minus 12, 2 degrees. Now to analyze this truss, we have to choose two redundant actions, one member force and one support reaction. That way we can make it. But remember, while you are making this statically determinate, your structure must be stable. And the definition of the truss is that the truss members should be arranged in a triangular fashion. Now, Euler load method for displacement, the revision of that one, it is having exactly the same configuration as that of the moment equation. In moment, let's go one by one. This method is based on the principle of virtual work. So the basis for this unit load method is principle of virtual work. Best suitable to find the slope and deflection of primary structure when subjected to external loads and unit loads. Displacement due to actual loads at any point is given by, this is in case of the axial loads we are talking about. Now here we don't have the integral sign. What is the reason? The reason is because the axial forces will be constant throughout the length of the member. In pendulum moment it was changing, and to capture the total now we integrated that because of the variation along the length of the member, but here it is constant. So here we don't take the integral. Dx, if you see, integral was at dx. Here Li, the whole length we are using. Here it was integrated for dx. Now P, it is the axial force. It is now analogous to the capital M value. How it will be calculated? It will be calculated when we subject the released truss under the actual load. So the member forces which will be coming, that will give you the capital P value, like we did for the M values in case of the frames. M1, M2, M3, that will be coming here. This will become our U value because of the unit load corresponding to the redundant actions. So it is the product of P times U now, like there it used to be the product of capital M times M. And EI is replaced by EA now, axial rigidity coming here. So if you see, the nomenclature of this equation is exactly the same as it was in case of the frames, but their M's were involved. Here now the axial forces are involved. Now note, when axial forces are predominant, then use axial rigidity EA instead of EI. So as moments are not involved, axial forces are involved, so we are using EA instead of EI. Now, flexibility coefficient elements will be the product of small u's now accordingly. If it is NM, so U will be also NM, the product of N and M values. If it is NN, so it will be N times N, like F11. So these U1, these will become. If it is F12, so these will also become U1 and U12, the product. So this way, we can find out the flexibility coefficient values. Now, where P are the values of member forces in primary structures subjected to actual loads, and U are the values of member forces in basic determinant structures subjected to unit loads. Now, any question? You see the resemblance now. Resemblance आप यहाँ पे देख रहे हैं. You see the resemblance between the axial and the bending moment के लिए जब हम करते हैं. So if you have any question, you ask me. Otherwise, I'll move. And it is just the analysis of the basic determinant structures.
सर ये I की जगह A क्यों इस्तेमाल करते हैं, इसकी समझ नहीं है.
I की जगह क्या?
A क्यों इस्तेमाल करते हैं सर जी? EA.
EA क्यों इस्तेमाल कर रहे हैं?
यस सर.
अच्छा, EA इसलिए इस्तेमाल कर रहे हैं ना, ये एक्सियल नॉर्मल फोर्स आपका जनरेट होगा ना. इट विल बी the axial force is predominant. I is related to the bending moment, and A is related to the axial force now. So when you have axial forces predominant, you will be using EA, not EI. Are you getting my point?
Thank you. Okay, sir.
एक्सियल के लिए आप क्या करते हैं? P divided by A करते हैं कि नहीं? P divided by A, you never do P divided by I. But when you go to the bending moment, so there M, Y, or I you use for to find out the stresses.
Yes, sir.
Okay, now analysis procedure. Analysis procedure is exactly the same as we did in case of the frames. The following steps should be followed to analyze the statical indeterminate truss using flexibility method. First, find the degree of statical indeterminacy. So external indeterminacy and internal indeterminacy, you find out. Step number 1 will be identify redundants accordingly and obtain BDS, and then compute the DRS values. Number of redundants will be equal to the degree of statical indeterminacy. So your number of redundants will be equal to the statical indeterminacy. Let's we assume a 2 degrees indeterminate problem here. Assume, and 2 redundants we will have to select. Now, remember this note now, when a truss is both externally and internally indeterminate, then choose redundant actions from both member forces and support reactions. DRS is initial support rotation and settlement corresponding to the redundant locations. Step number 2, now we need to analyze the basic determinant structure. Now, primary structure को आप किस condition के, for which conditions you are going to analyze? First, under the actual loads, which will generate the capital P values, and then under the application of the unit loads, which will give you your U1, U2, and so on values. This I is showing the members now for different members. I starts from 1 to N. So that subscript is coming from the member number now, and so on. So exactly the procedure is the same. If a structure is 2 degrees statically indeterminate, you will be analyzing 3 times. If 3 degrees indeterminate, 4 times. Now, here now we make this table now for the member forces. And how this table is formed? First, we write the members. Let's say A, B, B, C, C, D, and these are the members. Axial rigidity, EA, we write for each member now in front of that in the row. Length for AB, for BC, and so on. Forces in release stress due to actual load, actual applied load. So P values, P for member A, P for member BC. Remember, in case of the rigid jet frames, we did capital M for AB, then capital M for BC, and then capital M for other member. Then forces in the release stress due to unit load at redundant location 1. So that will give you U1 for member 1. Here you can see U1 for AB, U1 for BC, U1 for this other member, let's say CT, and so on. So U1, this is corresponding to the small m1 values now. And similarly, corresponding to redundant action 2, you analyze the structure and get these U2 values for each member. Next now, we find out DRL1 and DRL2. DRL1 there, if you remember, it was capital M times M1 dx or EI. Here it will be coming PI U1I LI divided by EAI. I remember it is the member number now. So it will be the summation from different members contributing. DRL2, it will be PU2L divided by EA. Like we did capital M times M2 dx or EI. Similarly, F11, F21, you can see F1, F12, it is the product of the U1 and U2. F11 is the product of U1, U1, and F22, it is the product of U2 and U2. Now, after this, we go to the next step and we write the compatibility equation. Now, flexibility coefficients are known, DRS known, DRL known, so we can find the unknown redundant actions. Once those redundant actions are found, we go and find out the member forces. So AM is equal to AML, AMR, and AR. We find out from where the AML values will be coming. AML value you will get from where you created the capital P values. AMR, first column, you will get from where you wrote the U1 values. Second column will come from where you wrote the U2 values, and so on. Already we found this AR in step number 6. Sign convention which we will be following in this method. Tension in member will be taken positive. And how we show the tension? When the forces are acting away from the joint. Compression in members will be taken negative. And when, how we show it? When the forces are acting towards the joint. When the forces are acting towards the joint, that will be the sign of the compression, and it will be taken as negative. We come to the actual problem now. Analyze the given truss using flexibility method. So here you see A, B, C, D. These are the joints now. Horizontal we have 20 feet, vertical we have 15 feet. At A we have a hinge support, B roller support, and D we have a roller support. This D roller is different from the B. This B can support vertical load and D can support horizontal load. Now, finding out the external indeterminacy, how many reactions we have? Two at A, one at B, and one at D. So for unknowns, we have three equations available for the whole structure. So R minus 3 will give you 4 minus 3. It means it is 1 degree external indeterminate. For internal indeterminacy, we were having M plus 3 minus 2J. So M 6 members, 3, it is constant, minus 2 times J, 4 giants. So 9 minus, so 1 degrees it is indeterminate. Total indeterminacy is 2 degrees. M plus R minus 2J, you can find out it will be 2 degrees. So it is externally 1 degree and internally. So it means we need to release one support reaction and we need to cut one member also. Now cutting member, now if you see, you can cut AD. So if we remove this member AD, still we have very nice triangular arrangement of this member. We have this, let's AD is removed. So we have ACB triangle, and then we have C, B, and D triangle. Or you can remove C, B, still we have the triangular arrangement, so it will be the truss configuration and requirement will be met. Support reactions, you can remove this horizontal reaction at D, or you can remove this vertical reaction at B. Also, your structure should be stable. Now here, let's we designate now, as it was externally 1 degree, so redundant action at D, to the right, we assume. This is our AR1 towards the right. And tensile force in this AD, we declare this as our redundant action, tensile force in member AD. This is the AR2. These are our redundant actions now. Now, if we remove these two redundants, our structure is becoming a primary structure, which is a release structure and basic determinant structure. So here we declare them equal to unknown and unknown. DRS1 and DRS2 corresponding to AR1, we were not having any translation, so means it is 0. AR2, we don't have any, so it is 0. Sometimes they can give you that this member AD, it is on fire, and due to fire, it expands, let's say, by 0.25 inch. Right? So then you will have to include that 0.25 as your precondition. Now tangent theta we take with respect to this AB going in the counterclockwise direction. So here sine theta, first we find out the theta. So theta will become tangent inverse of 15 divided by 20, which is becoming 36.86. Sine theta is a sine of this 36.86. These numbers now will help you in resolution of the members into the rectangular components. So horizontal reaction at D and member forces and member AD are chosen as redundant actions. We solve taking these as our redundant actions. When you go home, you take another support reaction as redundant action and take, let's say, member BC as your redundant action and solve this, and you will end up with the same solution. Now, this is our basic determinant structure. Now, you see here now, just a simply supported and having very clear two triangles now. This is a basic determinant structure. Now, P values will be generated. How P value will be generated? This structure under the actual applied loads. Actual applied loads were at giant C. So that will give you the capital here, step 1 you see, and then that basic determinant structure under U1, and then U1 means when the unit load is at redundant location 1. And then at redundant location 2, we analyze the basic determinant structure and get the U2 values. Here now you see to generate the capital M values, this is now. Now the trick is how you analyze this basic determinant structure. So first we find out the support reactions. How the support reactions are found? This 10 kip horizontal load, it has to be now put in equilibrium, has to be resisted at this support A, because this is a hinge support and having the capability to resist this 10 kip horizontal load. So 10 kip rightward, 10 kip is becoming leftward. Here you can see summation of fx is equal to 0, ha is equal to 10. We are calculating from this one. How we do it? We put this ha towards the right now. So ha plus 10 should be equal to 0. So ha is becoming minus 10. So this is how we put this minus 10. Now taking summation of moment about point A is equal to 0. So here you see this 10 times 15 minus VB times 20 is equal to 0. So VB is coming 7.5 and this VA is the summation of FY if we apply. So VA is becoming 12.5. Support reactions are found. Now how do we analyze the members now? Very easily we can do this. If we take this joint D now, we can find out member CD and member BD forces very quickly. At this joint, no external loads are applied, no vertical and no horizontal. So it means horizontally it is not balancing nothing. And vertically it is not balancing anything. So it means this BD force is equal to 0 and this CD force is also equal to 0. Just by observation you can say. If you start analysis of this member CD from this joint C, you cannot tell how much will be the member force. But if you take it from joint D, straight away you can say this member force is 0 and this member force is also equal to 0. Then coming to this joint A now, by observation, how can I analyze this? This diagonal AB is not doing anything. It is cut member. We are just showing it that it is there, but it is cut now, not resisting any force. This 12.5 kip, it is upward. So this member force, it should be downward. It should be towards the joint. If at A it is towards the joint, so at C also it should be towards the joint. Means this member AC is in compression. So we have found the direction. What will be the magnitude? It is balancing 12.5. So the magnitude will be 12.5 and it is in compression. Member AC is now analyzed. You don't need to draw this A and then show the vertical member, then the horizontal member, and then HA and then VA, and then writing the equilibrium equation. Straight away by observation you can do. But remember this observation, it is coming from the experience. You have to now practice these problems. Similarly, now coming to AB now, if you see here, 10 we found for the support reaction. So 10 is leftward. So this at A, this AB force should be rightward directed. So if it is away, at B also it will be away. Means member AB is in tension now. This gives you the direction. What will be the magnitude? Magnitude will be equal to 10 kip. So we analyze this one also. Member AB is also analyzed. Only diagonals BC is now required. Very easily you can find out the direction, the nature of this BC. How? Its vertical component should be balancing this 7.5 upward force. And when that is possible when its component is in the downward direction. Very easily. Now you see to keep this 7.5. And when that downward is possible, when this member BC at B, its force is directed towards B, not away, towards B, then that downward vertical component is possible. So this is how we fix its direction. Its vertical will be downward directed and its horizontal will be rightward directed. So this will balance that tensile force in this member AB. Means BC is also under compression. And very easily by putting the summation of Fx is equal to 0 and summation of Fy is equal to 0, we can find out the BC force. And this will give you the capital P values. Now here by joint moving, this all these member forces are formed. And then here those are shown here. Look, by observation I was telling that it will be same as 12.5 towards the joint. Here it is 10 away from the joint. Here this is 0, this is towards the joint and its magnitude. Now here member AB, if you see the length is how much it was, we need to go back there and see it was 20 feet. And these diagonals will be 25 feet. So you need to remember these things also. So now for member ABP will be 10. For BC it will become minus 12.5 because it is compression. For member AD it will become 0. Member AC it will become minus 12.5. For member CD it will be 0. For member BD the P will be equal to 0. So from here you can complete your P column now, P values for each member. Next now we subject this basic determinant structure under a unit AR1. Same direction, UR1. Quickly analyze, find out the support reactions. AR1 rightward, so AR1 here. It is causing a couple now, 1 times 15. So 1 times 15 divided by 20, which is 0.75. This is the balancing couple now. Applied moment was clockwise. This is now balancing one. It is counterclockwise, 0.75. Now, quickly we can analyze the structure. Here, if it is 0.75, so it will be away from the joint, this will be 0.75. This one kip, so away from the joint, it will be 1 kip. Here, these members, we can analyze this by taking joint D now. So 1 kip, so member DC will be also 1 kip, and it will be away from the joint. Away from the joint means it will be tensile in nature. Now BD, we don't have any vertical load. This is not doing, this diagonal is cut member, so this is 0 now. And from here now we have vertical and horizontal, so it will be the resultant of this vertical and horizontal. So you can find out. Obviously its direction will be towards the joint, means it is in compression, member BC. And this will give you your U1 values. So from here we get U1 values. This is when we do it by going joint by joint, and these are all those member forces formed out. Look, this is 0, this is 1, this is 0.75, 1, and this diagonal 1.25, which is the resultant of this 1 and this 1 square plus 0.75 square whole under the root, so you will get this one. And this will give you your U1 values. Next now, we apply a unit now unit action corresponding to the AR2 now. It was tensile, so we apply a tensile now, 1 kip. Now, how we analyze under this condition now? When you are stretching this member, you are trying to close these members, so what will happen? You will be inducing now forces in these members. Remember, it is not going to cause any support reaction now. Internally, this load will be distributed. Now, how can we find out the member force CD now? Look, its horizontal component will be leftward directed and vertical will be downward directed of this 1 kip. Already you have the components cos theta and sin theta, so you can find their magnitudes now. Its horizontal component will be balanced by the force in member CD. If it is leftward directed, so here it will be rightward directed, means towards the joint, and towards the joint means member CD is coming under compression. Its vertical component was downward, so at D, the member BD force will be towards up direction, means to balance this downward. So against towards the joint and towards the joint means FBD, it is in compression. You can resolve this into rectangular components. So horizontal component will become member CD force and vertical component will become member BD force. Similarly, here you can find out the member A, B, and CD. It is the same force we are resolving here in the rectangular components, and we can find their directions. And here you can find out member BC also, which will be the resultant of CD and AC force. So you can find its direction. And this way you can analyze all the member forces. Now here this is shown when we go joint by joint, and here now you show all these things, all the member forces, and this will give you your U2 values. Now we put them in the equations. Now here first we make the table. Here you see AB was 20, 20, this is diagonal, again horizontal, diagonal, and these are verticals, 15, 15. P values, we record the values here. Minus means it was compression. 10 means it is tension. Then U1 values, if you want to verify something, let's verify this one, minus 0.8, which is U2 and member CD. So let's go to member CD and minus 0.8. This is member CD. This is member CD, and here it is compression. So minus 0.8 is from here we are filling that value. Rest is now the DRL1 calculation. So here you see, this is the basic equation, PU1L divided by E. So for when I is 1, we have this first number. 20, it is coming from this L1 now. AB, remember the horizontal, it was 20 feet. P value was 10, it was tensile, and U1 value was 1. So order, it is not matching the equation, but here this is length we are writing first, then followed by P and then the U value. For member 2, which was diagonal, let's say member 2 is where? This one, member. Did we do any numbering? Anyways, this is, and match it. So this is for the second member, this is for the third member, 0 is from fourth, this is from fifth, and this is from the sixth member, contribution from all the members. This is when we calculate the F11, we are here at the DRL1. So here, from all these 6 members, with their appropriate signs, remember, length is always positive. So the first number, it is showing the member lengths. Second for the P values, and third for the U values. So all the 6 members contributions are coming here. DRL1, it is 450 divided by EA. DRL2 now, it is coming from the product of PU2 and times length. So here again, you see the length of all the members, all the 6 members, it is the contribution. So DRL2 is calculated. DRL matrix is now complete. 450 over EA and minus 360 over EA. Next, now we go and calculate the flexibility coefficient matrix. U1 values also already we have. So this is 20. Again, it is member 1 length, and U1 was 1. So 1 square. Then we have 25 times minus 1.25 square. Then 20 times 1 square, and so on. F11 is calculated. F1 is equal to F2 is calculated. You see the contribution of all the 6 members again, and F22 is calculated. So we have the F22. This is now the consolidated flexibility coefficient matrix. Next, now we go and write the compatibility equation. So compatibility equation is written. So AR1 and AR2. So here now we find out AR1 and AR2 means the support reaction at D, it is not in the direction we selected, it is opposite to that one, and AR2 member force is coming equal to 0. Here now we write Initially, we assumed rightward, so we are putting this now leftward, 5.14. Okay. Member force, it is coming 0, so we put this equal to 0. Now, rest of the member inductions we can find out from where. Now, this is AM is equal to AML, AMR times AR. So this is AM1, AM2, AM3, AM4, 5, and 6 here you can see. So these are our unknowns. Now, AML value will come from where we calculated the capital P values. AMR first column from where we calculated U1 values, and AMR second column from where we calculated the U2 values. So here now you can see. This is our AM1, so this is becoming now 10. Then we have minus 12.5 and then 0. You need to look at, keep an eye on the AM values. Now tensile we take initially as positive. So 10 minus 12.5 and 0 is here you can see. Then this was the AM4 was here, this diagonal AD. This is 0, so 0 is recorded here. Then minus 12.5 and 0, so minus 12.5 and 0. Next, AMR first column. So AMR first column will be from here, it will become 1 minus 1.25 and then 1, 0 is 0.75 and 0. And second column will be generated from here, from this one. So now here you see all these values. Now, when we do this matrix operation, all the values we have. So you see here AR, we have AMR, we have this now AML values also. When we multiply and summation, so it gives all the member. Now 4.86 AM1, so 4.86 here you see. This BC member force, it was our AM2, which is minus 6.0. Minus means it is compression towards the joint. So towards the joint, you see 6.08. AM3 was this member CD force. It is coming again compression because of this minus, so towards the joint. AM4 was member AD. Here again, you see here it is 0. So this is verification now. And already we found this as AR2. If you don't want to do this here at this stage, you can just skip it. AM5, it is compression now, minus 16.36, so minus 16.36 here. And this is AM6 now, 0, so this is 0. Now, this is analyzed, still we need to find out the support reactions. So support reactions here, now you have these member forces, you can take the summation and you can balance them here. But remember, these support reactions also you can find out with the help of using the flexibility, this matrix approach. How? Let's this vertical reaction at A, I take this as my AS1, support action 1. This horizontal I take as AS2. And this vertical reaction at B, I take this AS3 now. So you need to now pick the corresponding value for ASL from the capital P value and corresponding AMR from this will become ASR actually, member induction. Instead of the member induction, it will becoming support now. So ASR, I'm saying now, it will be coming from the U values now, the first column and the second column. So this is your assignment now. Use the matrix approach and find out these vertical and horizontal reaction at A and vertical reaction at B by using the matrix approach. Now, it is 2:08 now, so almost we are done with the time now. But I can go quickly over problem 2 and maybe problem 3 also. But the thing is, let's stop here. I'll stop my recording now. And me go there and stop the recording.